And do you see my first slide?
Yes, I can hear you and see your first slide.
So this is joint work with my PhD student, Frederik, and we are from Technical University of Denmark in Copenhagen area. And this is about our experiences teaching two courses on logic, one on logic and one more on automated reasoning. And we're using Isabelle in both courses. And there's a lot to say because we have taught one of the courses, the bachelor course on logic and logic programming, for me 16 years, not Frederik, but he's been TAing the last years. And it's a course with around 80 students per year, almost since the beginning. And we have a lot to say about that, of course. I should say also that in that course, like half of the course is our own notes about Prolog, ISO Prolog. Actually, we use SWI Prolog, but the half of the course is really Prolog. And that's really something the students kind of love even. But we also introduce Isabelle, and that we've been doing that for almost 10 years, just a little. And in the second course, which is a master course on automated reasoning, we focus a lot on the basic logic concepts. Also, it's classical higher order logic. But also on Isabelle. And that course is quite new. We had around 40 students per year for 2 years now. And the overlap between the courses in terms of students is that only like, I think 20 students from the bachelor course actually are the students on the master course. And that's also partly because our master program is international, where the bachelor program is in principle, it's given in English, but it's on a Danish bachelor in computer science, software technology. But the master course is really truly international audience, and half of the students on the program are coming from abroad. So also I should say that in the automated reasoning course, half of the course is going through the Isabelle Hall tutorial available, part of the Isabelle system. So I'm not going to talk about that, and I'm not going to talk about the ISO Prolog and the action. So actually we have a lot of programs in Prolog, also provers written in Prolog, and that's not part of what I'm going to talk about here. I should say the first course, the bachelor course, is focusing more on automatic theory proving. And actually, we are using a book there, the Mordecai-Benary book on mathematical logic for computer science. So that's also, in addition, they see a classical textbook on mathematical logic. So I'll move on to my next slides with kind of an overview. So in fact, we are using both Isabelle Pure as well as Isabelle Hall. The Isabelle Hall is the main part, but we actually spend quite some time setting up our own logics in the Pure framework of Isabelle, where you define your own axioms for like first order logic and high order logic, for instance. So I should focus here on just a few things, and I'll focus on two tools that altogether are more than 5,000 lines of Isabelle formalization. So it's not a very small theory that we work within, and it's actually from an Isabelle side kind of all integrated in one Isabelle Hall theory. That's the sequent calculus verifier and the natural deduction assistant. So these are online tools. You can go to the websites and play with them, and there are quite some help systems and examples and so on. But we should keep in mind that the students, they have basic knowledge of logic and also of particular systems. It's not straightforward for beginners. And what is special in these cases is that for this the sequence calculus and natural deduction proof systems, we have sound and completeness formal proofs in Isabelle of these logics and the proof systems. So that's what part of what we're teaching is how do you get to sound and completeness for these proof systems. And they're of course quite different, although related, the sequence calculus and the natural deduction. I should also say we have quite a number of other tools. For instance, we have also the students' proof assistance. That's another 5,000 lines of Isabelle and actually ML code. For that particular system, we are focusing only on the soundness, but that we have also in Isabelle. And since it's all in Isabelle and there's no web interface or tool around it, you have to go to the GitHub to just get the theory. And the student proof assistant is formally verified, like also the part of the proof system for the two other systems, and it's all integrated in Isabelle and in using a lot the JEdit and the ML facilities. So just to position the courses in the paper, we have quite a lot about the learning objectives and prerequisites and so on, but just to say a few things. So the two courses are formally quite separate and should be possible to take them independently, but I see clearly a connection, and I'm the sole responsible for the two courses. We can assume that the students know discrete math, some logic there, usual Tableau, and of course programming algorithms and some basic topics in more theoretical computer science and functional programming. When we get to the master level, the international students will not always be very strong in like functional programming. So that's of course a challenge if you want to work with Isabelle Hull, but they have to catch up on that. We have a number of courses on the master level that could follow the automated reasoning course, which is very general on logic and automation of logic. There's the logic for security, there's applied functional programming with advanced topics in functional programming. There's more formal aspects of software engineering, and there's also applications of logic in, for instance, AI and natural language semantics. So the courses are actually not very large, and keep in mind that in the first course we also have to teach the ISO prologue, and we also go through the Isabelle tutorial with all the exercises and many examples. There are 5 ECTS, so in our terms it's 13 weeks, and they have 2 hours of lectures and 2 hours exercises. We need to have that particular structure due to the way the whole system and the TA allocation works. So that's on that. Good, so I think I covered that. Just to give you a glimpse, this is a screenshot from the natural deduction system, where you have to get used to the particular way to write up and break down the proof. But at the top, you have the formula to prove. So this is the well-known Drinker paradox or Drinker example, which in a natural deduction system actually is a bit involved to prove. The thing is that when you have the proof there, you can see in the right corner here, you have a smiley, meaning that you have no missing parts. And if you click on that, you get the Isabelle formalization. You have manually to put it into, copy paste it into Isabelle, and then you have the whole verification of proof, and also the whole part of the semantics of first order logic in this case. So that's the integration. It's not in Isabelle, but it's something that the student needs to hand in the format that we can verify in Isabelle. there's a possibility to upload your proof on our servers, and a lot of examples and teaching explanations on the side. I'll not go into all the details, but just now let me show you the sequence calculus verifier. So that's a newer system. The natural deduction system, we have used that for quite some years with now hundreds of students. Also at the exam, they have to work in it. And similarly for the sequence calculus verifier, it's a quite different style. On the left here, you see what we call a shortened sequence calculus proof. It's on purpose that the students actually have to enter the kind of abstract syntax. For first order logic, we use the Boying indices, and of course they have the textbook and other materials. And when they work in Isabelle, they're not using the Boying indices, but we actually find it's a good thing for the students to learn, and it's working reasonably well. Also, actually, in this unshortened setting, they don't have to use the Boying indices, but when we get to Isabelle, that's what we're using in the formalization. And on the right, you see the general Isabelle proof that you can just copy and put into Isabelle and study. And of course, you can also work directly in Isabelle, but the template, the boilerplate you have to work with is a bit more substantial than in the unshortened part. So we have papers on both these systems and how the students are thinking about the systems. So just to go back to the natural deduction systems, that's actually not text-based. You have to click everything in, and that's actually also a good way to force the students to work in a structured way. And here's another formula that you are working on. You are presented with different options of the rules in natural deduction, and when you click, you move towards the end, and you have the proof. Once you've done the proof, it's here at the bottom. I've inserted it at the bottom right. There's a clear mapping to the proof, and that's also what the students will be working on in Isabelle Hull, or also actually just the first order fragment. And that's also where we use the Isabelle Pure, because we formalize a fragment of Isabelle Hull, and so the proof will the one on the left and also on the right, where we have added the names of the rules. That's working in our own formalization of higher order logic. So very briefly, here's the course plan. I don't have time to go into the details, and here again the whole part with the ISO prologue is not mentioned. One particular thing is that we actually have a number of assignments that are kind of mandatory, not formally, but it's evaluated as a whole. So in practice, it's mandatory, and you see it's very good to have regular assignments every second week. And this is structured along the book by Mortcré Benary that I mentioned. For the automated reasoning, it's grouped here in 2 weeks kind of topics. And we start out with something we call microprovers, and then we have the natural deduction system and our systems in pure, and then some axiomatic systems, student proof system I mentioned also. Just to say, on the axiomatic systems, we have soundness and completeness for precision logic and also for first order logic now. But here are some of the axiomatic systems where the students can work in Isabelle and see how to prove the soundness and completeness just of these, for instance, proof systems. This is in a paper that came out recently with my PhD student Esther Fromm and my master student on a session. So taking that further, the proof system behind the students' proof assistance is also axiomatic. That's the system by Taskis and others, and also the one used by John Harrison in his book on practical logic and automated reasoning. And that for that we have also a soundness proof and integrated in Isabelle, where you can make proofs both in apply style and declaratively. And also, if you want just a single slide with the semantics of propositional logic and approver, all shown to be terminating sound and complete, we have a number of options there that the students can play with, and for instance, export to Haskell. So conclusions, a variation of systems, in particular, I mentioned Medea and Sekau and SPA, and a lot of other formally verified proof systems and provers. It's all our contributions to the so-called ISAFOL project, formalization of logic, by Blanchette is describing it in this paper. And the overall conclusion is actually to use formal methods, use in particular proof assistants like Isabelle in teaching logic and formal methods. So in the end, we basically have no non-formalized things in the course. It's all formalized, and in this case in Isabelle. So thank you for listening, and I'm ready for questions.
Okay, well, thank you very much, Jørgen. Any questions from the audience? Okay, so we have a question from Tobias.
Good morning, Jørgen. Thank you for giving yet another advertisement for teaching with Isabelle. And as far as I understood you, what the students learn to do is to write natural deduction or sequent calculus proofs in Isabelle. Have you also considered getting them to do proofs about the meta theory of these proof assistants, like soundness or completeness of some proof system?
Yes, so in the course we present the soundness and completeness proofs. So that's what we have and my students have done. If the student wants, and that's actually examples also in the references here, if the student wants to consider particular logic, and that can be even also non-classical logics and modal logics, that we have to do in special courses and bachelor or master thesis or even PhD projects. I think in general, so it's not, the students will be taught the semantics and the soundness and completeness proofs using Isabelle because it's formalized in Isabelle. We have also on the side the textbook. We don't formalize it line by line, but there they can see an ordinary, what we call informal, but still, of course, quite precise soundness and completeness proof. I should also say that I mean the natural deduction, the sequent calculus proof. Okay, for the natural deduction, they learn how to do it in ISA and the relationship to the traditional, like pen and paper presentation. But for the sequent calculus, it stands alone. I think more. It's not like they learn how to do it in Isabelle, except by calling auto or things like that. Thanks a lot. Yeah.
Okay, thank you.
Okay, thank you. Any more questions from the audience? Okay, Lucas has a question. Go ahead.
Yeah, I think we have a similar course on automated reasoning for master students, and yeah, I'm just opened the sequent calculus and the natural deduction assistant, and yeah, I'm just wondering how to input a formula there, because yeah,
you have to go
stuck with it.
But if you click on the load and click on the example and just click take example 9, you will have an example. Yeah, So, but it should be explained on the help pages, right? Yes.
Okay, thank you, Lucas. One final question before we go into the break. Okay, Catherine.
Yes, I would like to know how do you evaluate students?
Okay, yeah. So when we have the Corona situation, it was an exam from home, and they had access to Isabelle and the internet and the tools. But actually, the standard way to do it is the formal exam is a 2-hour paper exam. And there they have to write the prologue and the other formal proofs. But also the assignments, they also contribute to the grades. So there's more information in the paper on the website. And if you follow the links, you can see also the course evaluations, they're public, and also the exam results, statistics, of course. Thank you for the question.
Mm-hmm. Mm-hmm.
Okay, so thank you very much, Jørgen, once again, and thanks to Tobias, of course,